Thanks again. Okay, welcome back everybody. We're going to continue with the delta method. I will go through the proof. I'll show you kind of an incorrect proof first, and then we'll fix it up. I think there's just some insight to get out of doing things a little bit wrong the first time. Then I'm going to move into Bayesian methods. So this is slightly out of order. They bring up Bayes in chapter 7, but I want you to have a whole bunch of different things in your artillery before we move into chapter 6. So I'm going to start Bayes, spend a couple lectures on that, and then we're going to move directly into chapter 6. So kind of starting with sufficiency. So very important concept. And so we're going to use that concept over and over and over again in this class. Regardless of who we are as statisticians, regardless if we're frequentists or Bayesians, sufficiency is a big deal. Okay, let's just begin with this proof. So this is what the delta method says. So if I have a random variable, yn, so this is a sequence of random variables that's converging to something. And it's converging in distribution. So, or if you want to think about this, if you're a convergent sort of person, this is also converging in probability. If it's converging in distribution, then the probabilities that we compute from something are also converging. We talked a little bit about the almost sure central limit theorem, and you have a paper, but we're not covering that in this class. So this is a sequence of random variables. And so one random variable that we all know about that has this property is the arithmetic mean. So x bar, n, I goes from 1 to n, xi divided by n. And as n gets bigger and bigger and bigger, this thing tends to be normally distributed. And in practice, we don't take it all the way to the limit before we use it as a normal. Usually we say something like n is equal to 30 is good enough, and this is normal. But keep in mind, that's not always true. Sometimes n has to be wildly larger. And I'll talk about that a little bit when we move into our example for Bayesian methods. But this is tending to normality. It never actually gets there. But it might be so close that you can use it that way. Okay, so if I have a sequence of random variables that has this property, I subtract off the mean. So this right here is the expectation of yn. And this right here is going to be the variance square root of it of yn. So the standardized version of yn tends to normality. I'll just point out there's no n's over on this side. So when I take n goes to infinity, all my n's are over on the left-hand side. This is the part I'll butcher in the proof the first time. I'll put my n's on both sides of the equation, and I'll try to make a point about it. But it says if this is true, then transformations of yn also have a central limit theorem that applies to it. So our g, in this case right here, is our Taylor approximation of everything. So we're going to start working with this linear approximation. The delta method relies on that. And we have to consider this remainder term. But we'll show that this thing is converging to something normal. Again, I pulled all my n's out right here. The book sometimes takes the sigma and writes it over here. So they square it out when they do that. It would show up here squared out as well. But we want the n's over on one side. So let's try to do this proof. So I'm just going to say, let's look at just this thing right here. Limit n goes to infinity of g yn. So our transformation. So I'll just write the limit over on the right-hand side. So this is g theta plus the linear term, g prime theta, yn minus theta, plus our remainder. Okay, so I'll just distribute this limit over here as well. And I'm thinking about this limit limit over on the first part is just acting upon the linear term. Now, I do understand I have all of my n's kind of not in the right place, right here. We'll fix this up in a second. So let me just say this is incorrect. But we'll get the intuition for everything, and then we'll fix it all up. So this thing right here, limit n goes to infinity, there's no n's over here. This is just a constant. So when I take the limit, n goes to infinity here, I'm kind of inclined to think, well, this is normally distributed. And in a practical sense, when we apply all of this, we would use it, just like what I'm about to write down. But in a mathematical limiting sense, this is incorrect. So this is going to a normal 0, sigma squared over n. Now I get it. That's going to collapse to 0, and we don't like that in our proof. So we're going to have to pull the n's over to the other side. Let's talk about this remainder for a second. So what do the terms in the remainder look like? They look like these. Sum, I'll just use a dummy argument, k. K goes from 2 to infinity, and all of the terms look like the derivatives. The kth derivative, centered at theta, divided by k factorial, yn minus theta raised to the k. And so where the n appears in the remainder is only right there. This stuff doesn't have any n's in it, so we don't even have to think about it. It's just some constant. So what does this term do as n goes to infinity? Let's think about something simpler. As yn goes to theta, the remainder term goes to 0. That's obvious. So if I plug in yn is theta, right there, all of those terms are 0. So what does yn do? As n goes to infinity, yn goes to theta. Why is that true? Because of this statement. Right over here. So the yns are going to the mean. So that's the law of large numbers, if you will. The central limit theorem says just a little bit more about that. It says how everything is distributed. Let me screen up for a second. And I won't sound so muffled. So this remainder, we're inclined to think, we don't need to worry about it, but we need to put a little bit more effort into this proof to see what's going on. And so this is incorrect because I have this n sitting over here on the right-hand side, and I haven't dealt with this properly. But we know that this thing is going to 0, this whole remainder term, as n goes to infinity, but we don't have a correct proof of this central limit theorem. And so we're going to change this up a little bit. Just give myself some room and fix this proof. So if I saw this on a qualifying exam, I would mark you down for it. So I want you to do it technically correct. Oftentimes I do things kind of intuitively first, and then I fix it. So this would be correct. I'm not going to write out every detail here, but you're going to see it, what's going on. Usually when I get to this point in the proof, I think everything's just fine, and I say something like, obviously. This ends up being true. And that's what mathematicians do. So if you have your PhD and you say, obviously, it must be true. But you're not allowed to do that yet. So you have to wait a couple years. So let's just look at this creature. Limit n goes to infinity. And I'm going to write out g yn minus g theta. And I'm going to standardize it all. Sigma over root n. and pull those ends over to the left-hand side of everything. So this is going to be limit. N goes to infinity. And I just need to standardize everything. I just need to scale everything by this standard air term. So I've subtracted off the g theta. So essentially what I'm doing is I'm pulling that over to the left-hand side before I even do anything. I don't need to justify that. There's no ends there, so no big deal. So this is just going to be this term, g prime theta, yn minus theta, divided by sigma over root n. So what I did to the left-hand side, I need to do to the right-hand side. Plus the limit, n goes to infinity. And I have to think about this remainder just a little bit more. So the remainder divided by sigma over root n. So I have to treat that the same way on the right-hand side as I do on the left-hand side. So I haven't changed anything. And so I can just look at what's going on here. So let's first treat this and see what happens. We know a lot about this already. So we've already said something right there. So this is converging to a normal 0, 1. When I multiply it by something, it just changes the scale factor. And so this is converging to a normal 0, but because I multiply by something, that's not 1 anymore. So this is g prime theta. And the part I always forget to do is to square everything, so don't make my mistakes. Now we have to think about this. This is our result. We want to say that's going to 0. We have to be a little bit more careful when we do this. So notice the terms in Rn, they look like they have this thing going on. Yn minus theta to the k power, where k is going to be greater or equal to 0. So if you'd like to write in this other part, g kth derivative of that theta divided by k factorial, you can write those down. So that's what all the terms do look like. So, oops, k is bigger than 2 in there. So all the k's in the remainder start at 2 because we've already absorbed the 0th term in the first term. That's what we're using in our approximation. So we've already argued that this term right here, yn minus theta, is going to 0. So we know that's going to 0. So because yn is going to theta. So that's as n goes to infinity. So we know these terms right here are also going to 0, but they're going faster. So the terms, this term is going to 0. That term right there is going faster because I'm powering it up. So something small getting powered up is even smaller, and it's much smaller. And so now I want to just think about this square root of n right here. I'll focus on this one. This thing in the denominator. This is also going to 0. And that's where we go, uh-oh, I have to think about this a little bit more. So if that was a constant down there, we wouldn't have to think about it anymore. We just use this result that this Rn is going to 0. But I'm dividing by something that's going to 0. And I have to think about how fast everything is going to 0. So this right here, these terms, I'll just write down the second term because this is the smallest term. Or sorry, this is the largest term in this sum. Everything else is going to 0 even faster than these terms. So second derivative divided by 2 factorial yn minus theta raised to the second power. So this is my largest term. Everything else is smaller than this, asymptotically smaller, and as n goes to infinity, they're getting even smaller and smaller. So I want to compare to sigma over root n. And I can make an argument pretty quickly that this is going to 0 faster than this. So how do I know? I already know this is going to 0. Now I'm squaring it. So I kind of added in an extra term, like 2 linear terms multiplied together are quadratic. And so when that's going quadratically fast to 0. How fast is this going to 0? Much, much slower. So if this was divided by n, right here, then those rates would compensate each other. So this would be the linear term right in here. But this is going to 0 faster than all of that because of this square. So I want you to think about that. The book walks you through that argument. But this is going to 0 much faster than that's going to 0. So again, this is going to 0. It'll collapse to 0. Now I'm multiplying by an extra linear term to make it quadratic. So yn minus theta. So I'm just going to write this out a little bit differently. Yn minus theta. Same exact thing. So I have this other term that's going linearly fast to 0, linearly fast to 0, multiplied together quadratically fast to 0. This thing is going to 0 at square root speed. And so I have an extra half power up in the numerator. And so I want you to think about that. If you'd like to graph it, you can do that. But I would say in my proof, obviously, that's going to 0 much, much faster. If this was being divided by just n right here, now I've got trouble. So if this was divided by n squared, this would be going to 0 faster, the denominator, and that remainder term would blow up on me. So you think about that a little bit, but it's basically just arguing through polynomials and how much they shrink numbers. So obviously, through that spiel, this is going to 0. Any questions about that? Hunter.
So how do we know again that yn converges to distribution to theta?
Because of this, our original assumption. So this is the if part. This is the then part.
Oh, okay.
So yn is going to theta. This is centered at 0.
Okay.
So it's part of the original setup. So we're using that. If that didn't happen, delta method doesn't work.
Okay.
Let me show you another case where the delta method does not work. So let's just look at an example. So just so you know, when I grade this thing, if I ever give it to you on an exam or qualifying exam, in class, if you write this out and you're a little bit sloppy about it, I'll probably give you next to full credit. On the QE, I will be more harsh about that. I want to see some PhD level thinking about this. So you'd have to argue through those rates. I would look to see that you made some argument. And as long as you're thinking about it right, you have this thing converging to 0 and the denominator converging to 0, and you argued that the stuff in the numerator is going to 0 faster. If there was some form of argument right there, I would accept it. So just make sure that you're treating Rn and dividing it by sigma over root n. And then you'll make all the theoreticians in the department happy. So I say a more correct proof because it seems like you can always make the proofs more and more and more and more and more correct. Prove every little thing. Might have to prove stuff about polynomials. I kind of give up after a while and I say, it's kind of true what's going on. So I think we could go all the way back and make the most complete proof and develop the whole real number system, develop calculus as we go. But at some point, we just start recycling results and we know things. So you'll decide where your limit is on that. Mine is there. So I think it could be treated a little bit more and talk about the rates of polynomial, how fast they go to 0. Okay. So here's an example of when the delta method doesn't work very well. So just write that out. Think about, I'll just say xi's come from a normal distribution with mean mu and variance sigma squared. So this is kind of nice because I don't even need CLT in all of this. If everything is normally distributed, and if I want to estimate the mean, I don't even need CLT. I get normality instantaneously. So maybe I want to know, I want to estimate the mean, and I'm going to use x bar to do it. So this is approximately mu. And we know that. And that's probably your best estimator. I wouldn't choose anything else unless I knew something about where mu's live. If you walk blindly into this problem, that's as good as you can do. If you happen to know from some sort of scientific rationale that mu is kind of in some interval range, you could improve this. So and we'll see that later on when we get into decision theory. Okay. Say we're interested in not mu, but g of mu. And my function will be a quadratic function. So for some whatever reason I'm interested in mu squared. I might apply the delta method to all of this. So if I were a statistician in the 1960s and you told me something like this, I'd say, well, maybe the delta method, I can write it down, it's analytically trackable, easy to compute, so I'll use it. So g of x bar is approximately, or I'll say the expectation of g of x bar. That's just the expectation of x bar squared. This is approximately g mu. I'll say mu squared. How close is it? We need to look at the variance. So the variance of x bar squared is going to be approximately equal to g prime mu squared times the variance of x bar n. We spent a couple lectures arguing this, at least one lecture. So the derivative of mu squared is 2 mu squared, and the variance of x bar is sigma squared over n. So we're thinking that g of x bar, this is just an approximation, granted x bar is normally distributed. I don't even need the limit in all of that simply because my xi's are IID normals. So I get to see n of those. But the delta method does have an additional approximation that goes into it. We're invoking the linear Taylor series. So this is only approximately true. This is normal with mean mu squared and variance. I'll write it out like this: 4 mu squared sigma squared over n. That's approximately true. Let's think about what happens if mu gets close to 0. a case where mu is 0. Then we have something like this. Is going to be approximately a normal centered at 0 squared, 4 times 0 squared, sigma squared over n. And this whole term is 0. That's a big problem. So if you gave me a normal distribution with variance 0, I wouldn't use it. So it wouldn't be very useful to me. So it doesn't show any uncertainty here. So it's really, this term right here can't be 0. For the delta method, to work. And we didn't stipulate that, but it was probably pretty clear. So I think we need an extra condition right in here. So I need to say something about what this term is. G prime theta cannot be 0 for this thing to work. G prime is 0, no variance in your approximation. I do happen to know something about x bar squared. So this is normally distributed. So x bar squared has some distribution. And I know Warren knows what it is, because he's told us before. What kind of distribution is it? Chi-squared? It's a chi-squared. So normal squared look like some sort of a chi-squared. This isn't the just standard chi-squared right here, but I have this additional factor that I need to think about, the sigma squared n term in all of that. So it's some chi-squared, and I could end up writing down which chi-squared it is. So it's always positive. I know that. And this approximation right here is no is positive anyway. You know, in fact, it's even worse because it's just stacked on 0. And so delta method doesn't work here. Let's think about what we could do. So gy n g theta plus g prime theta yn minus theta, and then some other terms. G second derivative theta divided by 2 factorial yn minus theta squared. And then I've got these other terms right in here. G cubed over 3 factorial yn minus theta. Let me just make this a dummy argument. I'll cut all this stuff into a sum. K goes from 3 to infinity. So if this thing is 0, I wouldn't want to use the normal approximation to all of this because it's not a normal distribution, it's degenerate. But I might go to this term right here. And I might look at the second order term and then just think about this stuff is the remainder. So then I might compartmentalize and say, let this be the remainder. And some people have done this. I've never actually seen this used in practice, but I certainly know people talk about it, and it's in your book. And so the second order delta method applies when g prime is 0. So if g prime is 0, then you start thinking about this second order term. Of course, this thing can't be 0 for it to work. So, but this thing isn't normally distributed. This right here is a chi-squared. So that stuff looks about normal. So this stuff right here has some sort of chi-squared distribution. It's getting scaled. So some chi-squared disk. In the second order delta method, is a chi-squared approximation to everything. They use the second order term. Why not use the second order term in all cases? You have a better Taylor expansion, but if this wasn't 0, this is normally distributed, this is chi-squared distributed, and you would add together a chi-squared distribution with a normal distribution. That's certainly some distribution. I don't know what it is. And so back in the 60s, people didn't know what it was, and it wasn't entirely useful to them. And that's why you don't always just add in all the other terms, because they don't have a distribution that's easy to work with. The idea in the delta method was it's easy to apply. I would certainly use the delta method as if I were trying to prove something asymptotically, but it depends on the problem at hand whether or not I would use it in practice. And so I'm going to leave it here. We're not going to cover the second order delta method, but have a read through it. I think they talk about it for a paragraph or two. They tell you what that chi-squared distribution is, but I don't think that I'm going to ask you too many questions about it. What I do want you to say, though, if I ever ask you to prove anything about the delta method, is make sure you stipulate that. So one of your conditions, your necessary condition to apply the first order delta method. So anyway, I think this will be a little bit more soothing once you code it up on a couple examples and see how well it works. And I'll be walking you through that in a future homework assignment. That's it for now on the delta method. Any questions before we move into Bayesian methods? Sweet. Okay, now the plastic part. We'll jump into chapter 6 very soon after this sequence of lectures, and now we're moving. Bayesian methods. Bayesians apply Bayes' theorem. Another way to say that is we penalize the likelihood. So Bayesians are always operating on the posterior. How do we get the posterior distribution? I'm going to think about X as just some collection of random variables. So we end up usually just writing down this is going to be equal to, I'll just say f of x given theta. So this is the formula for the sampling distribution. It's not the sampling distribution because over on the left-hand side, theta varies. So we need a different name for this function that we're actually playing around with. F of x given theta, pi theta, d theta. And you're integrating over the entire space of theta. So that's what this is supposed to represent. So if theta would live between minus infinity and infinity, these bounds would be minus infinity and infinity. There's no thetas in the denominator of the equation because I've integrated them out. So all the thetas are just right up here. And so this distribution is telling us about how theta varies across its space. And so theta is the variable over on the right-hand side. I usually don't use this notation. So because when I use this notation, I think that the bar means everything on the right-hand side is fixed, but theta is really varying. So I don't like the inconsistency of my usage of the theta. So I invoke a different notation for all of this. But when I take the formula for the sampling distribution, I plug in data, and I let the parameter vary. That's obviously not the sampling distribution anymore, but algebraically it certainly looks like it. So we usually call this the likelihood function. So likelihood. And this is just notational. That I might come up with a notation where f of x given theta, and this is going to be theta as variable, but x is fixed. And we know that sampling distributions have theta fixed, and the data is the variable. So I'm going to just write down that when I end up making theta variable in this equation, and x is fixed, I'm going to use a slightly different notation for that. This is my notation. However, I see people write down that's the likelihood function, but they were just talking about this function as the sampling distribution. So for me, f usually means x is variable. So again, this is all just convention. So it's notation, and if you don't like the notation, you can come up with your own, but you'll probably confuse people. So this is variable. This is fixed. I like this notation. I prefer it because now my bar tells me what I know and is given in the problem, and over to the left-hand side, that's the variable thing. I want to make a distinction that if I were thinking about the sampling distribution f of x, x is a random variable. It's not just variable. It's not just a function of x, but it has certain properties. I.e., if I integrate over it, it adds up to 1. This please.
If the theta is variable and then x is fixed, is the f of x given theta is joint density of theta, or
it's not. So that's what I'm talking about. It's one of them's fixed. So when I write this down, x is fixed in this, theta is variable. I don't like that notation, but you do see people use it. So it's not joint, but rather theta is variable. So I don't want to recycle this notation for f, because usually I like that to mean sampling distribution. So again, we're just agreeing upon rules for the notation, and that's it. So there's nothing to think about, there's just something to accept, what the notation represents. And I want, when I write this down on the board, I might need to change the rules and say whether or not this is the variable thing or that is the variable thing. And so instead of doing that, in telling you something like this, theta variable, but x is fixed in my equation, I'm going to redefine the notation. I'm going to use an L to specify theta is the variable thing, and I'm plugging x in. Okay.
So just to clarify, the f of x given theta, you're calling that the sampling distribution
It
formula?
depends which one's variable and which one's fixed. And that's what makes this hard, because when I write it on the chalkboard or the whiteboard, you don't know until I tell you.
Okay.
So to be more clear about it, I'm going to redefine the notation. And I'm going to let you know. So usually when I use f of x, I think that f of x given theta, I think that means x is variable. But if you told me, you're allowed to use f, and I'm just going to tell you you're allowed to change the definition of what's variable and what's fixed, I don't really like that just because it's confusing. So I want a notation to specify. So again, it's just accepting the nomenclature. I understand that this is wildly complex for people. You know, I've seen this before. Steven.
So what's the pi theta function?
That's the prior distribution. So this is the prior, and we'll talk about it in a second. This might represent your knowledge of theta going into everything, but it could also represent your ignorance about theta. And so I don't like calling it the prior distribution myself. If I could go back, I would change that terminology altogether, because it presupposes that you know something about theta. But it might be the case that I pick that distribution for mathematical properties that I'll get out of my posterior. And what I need to do is I need to look at the likelihood first and see what the meaning of those parameters are. And so it's really a question of, did the prior really come first and then I collected data? So you don't have to think about it that way. So it could be the case that I got my data, I started thinking about what those parameters meant, and then I constructed a prior distribution so that my posterior has a property. I'm thinking about the prior before I'm thinking about the posterior, or I'm thinking about the posterior before I'm thinking about the prior. So, you know, it's kind of one of those chicken and egg things. So it's like, which one came first, the prior or the posterior? The chicken and the egg problem is easy to answer. We know which one came first. I'll let you guys answer that. Danielle's like, what? So I know which one it is because I studied biology once upon a time. But in Bayes, depending on how you think about it and which version of Bayes you're invoking, will tell you which one came first. But the language is prior distribution. It's the egg. We'll talk about evolution later. So it didn't just start that way. So it changed over time. At least that's modern evolutionary theory. Let's not get too sidetracked with all of this. Let's look at an example. Oh, I will say what I usually write in terms of my notation phi theta given x is going to be equal to the likelihood times phi prior. Likelihood times prior, and I integrate out theta. The downside to this notation is it doesn't look like Bayes' theorem. It looks different. But this is what a Bayesian's doing, is they're weighting the likelihood function. That's what all Bayesians do. There's other groups of people that call themselves penalized likelihoodists. So they have some sort of constraint or penalty on the likelihood, i.e. they're weighting it. So for me, they're Bayesians. But they might not call it that. So again, a lot of this is just disagreement over terminologies and how we think about things. But I think a lot of times people are doing things that I would call Bayes. And they wouldn't call it Bayes, and then we would just argue about what we're calling it. I would let it go, you know, if I were you, but we'll still talk about it a little bit. Let's look at an example. And I'm going to have you play around with this example when you do your simulation studies. So this will appear in your life soon. But let's say xi's are coming from a Bernoulli distribution with parameter p. And I'll be polite, and I'll tell you that p lives between 0 and 1, and the xi's are elements of 1 and 0, where the 1 happens with probability p, and the 0 happens with probability 1 minus p. So the thing we're used to. So if everything's IID, I would know how to form the joint distribution. So the joint sampling distribution is, I'll write it out like this, f of x given p, so p is acting as theta, it's my unknown parameter, This is going to be equal to, I goes from 1 to n. This will look like p to the xi's, 1 minus p to the 1 minus xi's. Okay, so I'll just point out that p x, 1 minus p to the x is equal to either p or 1 minus p. This happens when x is equal to 1. Oops, this is a 1 minus. This happens when x is equal to 0. And so this is just a compact way of writing out what I just wrote out over here. So I use that form right here. So this might be f of x given p is a sampling distribution. How do I get the joint in an IID case? I just product it together. I multiply those probabilities into each other. The likelihood function looks like this. Again, this isn't a distribution. It might be something that you could turn into a distribution, but without me invoking certain considerations, it's just a function. So the likelihood function looks like this. Likelihood of p given x they're the same, right? Stephen's got the right answer. No, they are not. So it looks exactly the same on the whiteboard, but Stephen knows that these are the variables. And these are the variables here. So this is my point. It looks the same, but it's different, and wildly different. So in terms of a sampling distribution where these vary right here, the x's are 1s and 0s, this is a very discrete thing over here. It's a function of the x's, and those are discretized. They're 1s and 0s. This is a continuous function of p. So they don't even look the same at all. They're wildly different from each other. So I can draw a histogram for this thing right here to show you what it looks like. But this is going to be a continuum that lives between 0 and 1. So they're wildly different things. And I like to start out with this example. When you start with the normal example and you think about x's, they're continuous, living between negative infinity and infinity. And mu is continuous, living between negative infinity and infinity. And they look rather similar, but this is a good compelling example because they're totally different in this context. So I'll also point out that likelihoods don't have a property that they have to integrate to 1. So, however, my sampling distribution, if I integrate over x, over the whole space, this has to add to 1. But this doesn't need to be the case. My likelihoods don't need to add to anything. They just need to be positive. And so it's not the case that that integrates. And in fact, likelihood functions are self-relative. So you compare values in the likelihood to other values in the likelihood. And anytime you touch a likelihood, it comes in your equation through ratios. You can kind of see this in Bayes' theorem right here, that there's always going to be a cancellation right in here. So I can make this proportional to any number. So I can make it proportional to anything where this is going to have to be positive. So likelihoods can be multiplied by any positive number, as long as that's positive. So if I multiply this by some arbitrary positive number, I do it in both the numerator and the denominator, they cancel out. So points on a likelihood function I compare to each other. So if somebody said the likelihood of something was 0.9, I wouldn't know what that means. It wouldn't mean anything to me. So when I watch shows like CIS and they say the likelihood is 0.99, I'm usually chuckling and going, is that good? I know what they mean. They meant to say probability. Of course, that joke gets old with everybody else, and I'm chuckling over here to myself. I need a Bayesian in the room to snicker with. Let's just think about this function. So this function right here is, another way of writing it is p to the sum of the xi's, 1 minus p, n minus sum of the xi's. And this function only depends on the x's through the sum of the xi's. We'll learn later on that that is a sufficient statistic. So, and in fact, this is the smallest dimensional sufficient statistic. So the xi's is a vector of n numbers, but sum of the xi's is a scale. And so we kind of like that compression of information. Does anybody recognize this function right here? Do you have a name for what that looks like? It's not a binomial, because this thing is binomial, x is, but as a function of p, it's not binomial.
Is it a beta function?
It looks, that wouldn't be the word, because a beta function, that name is already taken.
Oh.
So that's the integral over that thing.
Right.
But this looks like the kernel of a beta distribution. And we have to answer which beta it is. We'll come back next time and write this down, discuss beta distributions, and then show the next step as to what a Bayesian does with their prior and how they construct their posterior, and how that posterior depends on the arguments in their prior. We'll look at a number of different examples. I'll run a simulation for you, and I think you'll start to like what happens in this example. Very nice. So I don't like to invoke the normal distribution for approximating p. I like to treat everything as a beta distribution. And so there's a big difference between the way a Bayesian will handle this problem and a non-Bayesian. So let's pick up next time. We'll start with this example. I'll show you some simulations. We'll discuss the impacts of the prior and get kind of a feel for everything. And then I'll tell you where this next homework problem is going to go. Just as a reminder, I'm going to give you new homework problems this Friday. We'll do a review session on Monday. The deadline for the current homework, you can turn it in on Wednesday, but hopefully you've moved through it so you can get started on the new problems. So everything's going to start to stack up here. That's it for now, you guys, so thanks so much. And enjoy the sun today. It's going to be 61. So here, obviously, look at the weather report. So he's been dying to come up. So I'm going to go out and play myself. So go enjoy it. We might not have it for a few months. Fun.